Today's goal is to name the domain of composed functions. Keep in mind domain is x values, like which x values are you allowed to substitute into the function, and composed functions are the result of substituting an expression or a function into another function. Let's start by taking a walk down memory lane and reviewing the domain restrictions of each of the function families we've worked with so far this year. Let's start by thinking about quadratic functions. Well, quadratic functions look like this. They travel forever to the left and forever to the right, forever up, but up is y values, and today we're just focusing on x values. And so we would say that they have the domain negative infinity to infinity, which is the same as saying quadratic functions don't have any restrictions. They can use any x value. Well, what about polynomial functions? Polynomial functions of even degree look roughly like this. Maybe they've got some weird sort of loops in the middle. And so again, they have no domain restrictions. Cubic functions and other odd degree functions will look like this. So really all of these functions are traveling forever to the left and forever to the right. And so for polynomial functions, they likewise have no domain restrictions. Okay, let's think about rational functions. Well, rational functions look something like this. And rational functions are interesting because they've got asymptotes. So let's say this is a, right? And so the domain of this function would be x is not equal to a. Or equivalently, negative infinity up to a, not including the value a, and the interval from a to infinity. So a, whatever the x value of that vertical asymptote is the one x value you cannot put into a rational function. And we know that's true because rational functions look like f of x equals something over something else, right? You're dividing. It's a ratio of polynomials. And when you come up with division, we know that you can't divide by 0. That's your restriction. Okay, let's consider now radical functions. And radical functions look like this. They've got a vertex, which we like to think of as hk. And so their domain is the interval from h to infinity, including h, since h is the value of the vertex, and the function does include that vertex. So a radical function's domain is restricted by what you can put in the square root. Well, we know that to be true because you can't put a negative number under a square root unless you're willing to deal with imaginary numbers, and we haven't learned how to graph imaginary numbers. So let's look at exponential functions. Exponential functions look like this. They have a horizontal asymptote, but let me make that a nice smooth curve. They are continuing forever to the left and to the right, and so they have no domain restrictions. And then finally, our friend trig functions. We know the sine function looks like this, and cosine function looks like this. Oops. And in both of these cases, whoa, sorry about that, they continue forever to the left and the right, and so sine and cosine functions have no domain restrictions. That's not true of all trig functions, but sine and cosine functions have no domain restrictions. So if we're going to recap, here's the big idea. The only functions that have domain restrictions are rational and radical functions. And for a rational function, you get a restricted value when you try to divide by 0. That's undefined. Like, what would it mean to have groups of size 0? It just doesn't make any sense. And for a radical function, the domain restriction is that you can't put a negative number under the square root, unless you're going to graph complex numbers, and we just haven't learned how to do that. Okay, so let's look at, I'm calling this example 0 because this would be sort of a review problem. This isn't a function composition necessarily. This would be a problem you might have seen earlier in the year. If we want to know the domain of this function, it's rational. I'm immediately thinking I can't divide by 0. So 5x plus 3 cannot be 0, which is the same as saying 5x can't be negative 3, and therefore x cannot be negative 3/5. This is your domain. If that doesn't really resonate with you, then maybe write it in interval notation. We're saying that x can be absolutely anything other than that one single value, negative 3/5. And this next example is a radical function, and I know what's under the root, the radicand, must be greater than or equal to 0. So x must be greater than or equal to 4. Here's your domain. Again, feel free to express these in interval notation or as an inequality. These are both inequalities, right? Not equals inequality. Okay, I think you're ready for function composition. State the domain of the composed function g of f of x for each pair of functions given. So let's start by composing. G of f of x means I need to put the function f, this entire expression, into the function g every time I see an x. So I'm going to write sort of my shell with an open set of parentheses. I'm thinking, yeah, let me double check. Yes, this does take the shape of g. And inside that parentheses, I'm going to substitute the expression negative x squared minus 3x. Okay, I want to find its domain. What kind of function is it? It's rational because it looks like a ratio of polynomials. Do rational functions have restrictions? Yeah, they do. You can't divide by 0. So I can actually ignore the numerator. It's irrelevant to finding the domain. If all I want to say are which x values can you use, well, negative x squared minus 3x minus 24 simply can't be 0. Well, now this is a quadratic inequality, which I can solve by factoring. Notice that the x squared term is negative, and so I'm going to factor a negative sign out of all 3 of the terms, or you're welcome to use the quadratic formula. And then I'm thinking, okay, I would like to factor this. I want 2 numbers that multiply to 24 and add up to 3. 2 and 12 won't work. 3 and 8 won't work. 4 and 6, 1 and 24. Yikes. Well, since it can't be factored, let's use the quadratic formula. I'm going to choose to do the quadratic formula on this inner piece because it just has more positive signs. You can use the original inequality. Either way is fine. So I have x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Let's substitute. And again, we're going to use the order of operations. I would get in the habit, of putting every substitution in parentheses. It'll just help us not make as many mistakes. I believe this is 96 all over 2. Oops. And so we have negative 3 plus or minus the square root of 9 minus 96, so that would be negative 87 all over 2, which would be an imaginary root. And so since it's imaginary, it won't actually ever touch the x-axis, and so we can say that the domain is from negative infinity to infinity. Again, we're saying that this quadratic has no real roots. It would look, for example, something like this, right? It's concave down because the leading coefficient is negative, and it just won't touch the x-axis, so there's no danger of dividing by 0. Okay, let's take a look at our next example. We've got 2 more left, and we want to find the domain of g of f of x. So let's do it. G of f of x means I'm substituting this function f into the function g. Oops, sorry. We'll take the whole thing. So we have, I'm going to write out sort of that shell of g. Yep, indeed that matches. So we have negative x squared plus x plus 2 inside that square root. And I'm thinking to myself, okay, which kind of function is this? Well, it's sort of radical, sort of quadratic, but I notice the radical piece, this right here, means that the restriction is, I can't divide by a negative number, so it must be that negative x squared plus x plus 2, whatever is under the square root, must be greater than or equal to 0. Interesting, I've landed myself with a quadratic inequality again. And again, that leading coefficient is negative, so I'm going to factor the negative sign out. Maybe this time I'll get lucky and be able to factor it. It's just a little bit faster. At this point, feel free to either draw a graph, label the roots, Notice that I want places where my function is greater than or equal to 0, and so that would be this region here, including the roots at -1 and 2. Or, feel free to make a quick sign chart. We know the roots are -1 and 2, so for x plus 1, it'll change signs here. And for x minus 2, it'll change signs here. And so the product, just be careful, it's the opposite of the product of these two. So it would be a negative times a negative times another negative would make this negative. A positive, negative, negative would make this positive. Positive, positive, negative, negative. Let me just double check those. Okay, and then again, we want places where the function is greater than or equal to 0. That means, where is my function positive? Where does my function equal 0? So whether you solve this quadratic inequality graphically or algebraically, you know that the solution is the interval from -1 to 2, including -1 and 2. Okay, one more example. Again, we're trying to find what is the domain of g of f of x. So let's just figure out what g of f of x really is by substituting the function f into g. So this is just the sine of 2x. Oh, what a relief. Sine functions don't have domain restrictions. They continue forever left and forever right. And so this function will have domain -∞ to infinity.